We didn't pay too much attention to this when we first looked at limits. We're going to revisit limits at infinity. So some reminders about limits. Limits either exist or they don't. So if I take the limit as x approaches some number a of some function, and we claim that the limit is L, right? So L is some number. Which means the limit exists. Now, it's possible for a limit to not exist, and that can happen in a few different ways. So sometimes limits don't exist. So it could be I take the limit as x approaches some number of a function, and we find that it grows forever. So example of that is if we took the limit as x approach 0 of 1 over x squared, and I pick x squared and 0 because I don't have to worry about right or left because I'm squaring it. Squaring it always gives me a positive result. So I have a denominator that gets smaller and smaller and smaller, and what we should find is the numerator gets bigger and bigger and bigger, and so we would usually say, hey, infinity is the answer here. But be clear here, infinity is not a number. This limit does not exist. However, the infinity tells us how it doesn't exist, so we can be specific about how it doesn't exist. So that's one way a limit does not exist. Another way the limit does not exist. Consider the limit, and we're going to throw an infinite limit in here this time to get into this section, of the sine of x. And so thinking about the sine of x for a second, graphically, right, it's this wave. And it always ranges between, wrong order, 1 and -1, right? So it's bounded in there. So this does not exist because it doesn't settle down. So a response that's common to limits like this is we just say, hey, DNE does not exist, and it's because there is no fixed number it settles on. As x increases. All right, another way a limit could not exist. Consider first the function f of x is equal to the absolute value of x. And absolute value of x, remember, is a piecewise function. The absolute value of x is x itself if x is greater than or equal to 0. Right? If I plug in a number like 0 or 1 or 2 or pi, I get 0, 1, or 2 or pi back. However, if I plug in a negative number like -2, I get 2. So I get the opposite of the number I started with. If x happened to be less than 0, that is a negative number. Next, think about the derivative of this function. F prime of x, what does that look like? Well, to get that, we have to look at the piecewise function. So the derivative of x would just be 1, and that happens if x is greater than or equal to 0. However, if x is a negative number, the derivative of negative x would be -1 if x is less than 0. So that's the piecewise definition of the derivative of the absolute value of x, right? So again, this is the derivative with respect to x of the absolute value of x. Now we think about the limit of f prime of x. So what is the limit of f prime of x as x approaches 0? Well, in this case, we got to break that into two parts. What's happening on the left and what's happening on the right. So I'm going to take the limit as x approaches 0 from the right of f prime of x, and I'm going to compare that to the limit as x heads to 0 on the left of this f prime of x. And on the right side, that's the positive, the non-negative values here, that limit is 1. On the left side, that limit is -1. And when I try to put those together, I have a problem because they're not equal. So that means the limit as x approaches 0 of f prime of x does not exist. Okay, so we got a few different things that can happen. Either the left and the right don't match, limit doesn't exist. Or the limit never settles down to a particular number, does not exist. Or the limit is infinite in some way, which is a special way to say it doesn't exist, but we know it's increasing, right, forever. So there's 3 different ways a limit does not exist. We're focusing in this section on limits where x is approaching infinity. So let's just play with some more examples of that. And you've done some of these before. In a pre-calculus class, this was described as end behavior of graphs. Functions. So in that case, we would look at what's the limit as x increases forever as we go to the right of the function. What's going on there? Or the limit as x goes to the left forever, what's the function doing? All right, so those are the 2 ends of the function. And this was looked at with polynomial functions. So for example, we might pick a function like f of x equals -2x squared plus 3x plus 1. And we want to know the end behavior here. And so we take the limit as x increases of all of that. Now, we had a rule that said you can break this into 3 different limits if each limit exists. And the only limit that truly exists here is the 1. So I kind of got to think about this holistically. And here's the intuitive way to think holistically. So here I have x is getting big x values. And if x is getting really big and we compare a square to a not square, the square dominates. Right, so big numbers, 1,000,000. So this is 1,000,000, this is 1,000,000,000,000. What's 1,000,000,000,000 look like, right? So if x is 1,000,000, then x squared would be 1,000,000,000,000. Right, which is what, a million, billion, let's see, no, this is million, that's billion. That would be 1 trillion, right? So they're not even comparable. X squared is so much bigger, right? If we were to graph the 2 of these on a number line, here's 0, here's 1 trillion, then we would have to make 1,000,000 marks from 0 to 1 trillion. And the first one of those 1,000,000 marks from here to here is 1,000,000. And there's not enough pixels on my screen for me to draw that. So on this screen right here, x would be right, look like it was sitting right on top of 0, okay? So point. For big X, a square is way more powerful. So that means the limit here is approximately equal to, for big X values, and I am using big X values, this is approximately equal to negative 2x squared. And so the negative 2, I can kind of pop that out. So this gets infinitely large, but in a negative direction. So that's negative infinity. Right, so that's the kind of end behavior thinking we're looking at. So polynomials are pretty straightforward. We kind of think about the sign and whether, ooh, I lied there. If I square, no, I didn't lie. If I, yeah, all right, get it. We're good there. Let's move on to another one. Rational functions are more interesting, and you guys in pre-calculus developed a bunch of rules about that, and those related to the powers. So let's consider f of x equals 2x squared plus 3x plus 1 divided by 3x squared minus 7x plus 2. So what happens in a situation like this if we try to take the limit as x gets large of this fraction? Oops, 2x squared, sorry, 3x plus 1, 3x squared minus 7x plus 2. We have the similar polynomial idea that the highest power really takes control of this thing. So this is approximately equal to the limit as x gets huge of 2x squared over 3x squared. And the x divides out, so that should be 2 over 3. So if the powers have the same highest degree, then what we should get is the ratio of their coefficients. Now, another cool way to look at this is to think about the limit as x goes to infinity of 1 over x. And as the denominator gets bigger and bigger and bigger, the whole fraction gets smaller and smaller and smaller, and this one right here heads to 0. So this is a very important, useful fact. And it doesn't matter if I have an x there or an x squared or an x cubed, it's still going to go to 0. So there's kind of a cool trick to problems like this that we can use elsewhere, and that is to divide by the highest power. So I'm just going to reconsider this in a slightly different way. Let's write it green first. So the limit as x approaches infinity, as x gets big and bigger and biggest, I guess there's no biggest. And what I want to do is I want to take each of these terms and divide it by x squared. So I'm going to have a 2x squared over x squared plus 3x over x squared plus 1 over x squared. Same thing in the bottom. 3x squared over x squared plus, oops, minus 7x over x squared plus 2 over x squared. And this cleans up just a little bit. This becomes, the numerator is now 2 plus 3 over x plus 1 over x squared. And in the bottom, I have 3 minus 7 over x plus 2 over x squared. And then I consider the limit as x goes to infinity. Well, as x gets bigger and bigger, 3 over a bigger and bigger number, that's going to go to 0. 1 over a bigger number, because I'm squaring it, that's going to 0. That's going to 0. That's going to 0. And the only thing left here, only things left here are the 2 over 3, which is kind of cool. All right, so we just ran out of time for fun with math. Let's take a look at due dates for a second. We're still a little behind the main schedule, so I am going to see if I need to adjust a due date here. 7/6 is due today. I'm going to shift that one to tomorrow because we still have a couple more examples I wanted to do there. But I've covered all the basics there, so the homework shouldn't be too bad. So if you didn't finish shapes of graphs, get your butt in gear, get that done. start working at limits on infinity. Read the book, please. There's very good stuff in there. And that's it for today.